time you have 7 homework problems assigned.
Yeah.
Okay, so let me just get my. So this is all mostly, I think, I did look it over briefly. Yeah, I don't think this has anything to do with waves on strings anymore. This is all about sound as it moves through air. So this is. Okay, so when I look over, like in the beginning, number 4 alludes to the idea that the speed of sound is different depending on the temperature.
Okay.
In fact, the speed of sound depends on if the medium is gas or solid. I don't see any problems in your assignment that talk about the motion of sound through a solid, but you should know sounds can travel through gases like the air that we live in, and also the sounds can move through solids.
Yeah.
So sound in general, I want you to remember, do you recall what kind of wave sound is? Or first, let's start with, what are the 2 kinds of waves in general? The names for 2 kinds of waves.
Transversal and longitudinal.
Yep, good job. And longitudinal. Do you remember which one of these sound waves are?
Longitudinal.
Yep. And so transverse, remember, looks like this.
Mm-hmm.
But longitudinal is more like these kind of spheres, like that are shells.
Yeah.
And then these areas are very highly compressed. And then the next band would be, so let me go back. So this section here, well, this section here is called the compression.
Yeah.
So the air is very tightly packed.
Mm-hmm.
Which means the density of the air is high here. And the pressure of the air is high here. Because when you compress air by jamming air into a fixed amount of space, more and more atoms get squeezed into the same amount of space. That's how you build air pressure. And so you're jamming them in. You know, let's say air molecules are originally this far apart. Well, if you decide to move this one in and move this one in and move this one in and move this one in so that now they're this close to each other, then the density is greater because there's more air molecules in a smaller amount of space, where before those same 5 little circles I made were in a larger amount of space, right?
Yeah.
You know the idea of density?
Yes.
Okay. And so that's what produces when they're forced into a small amount of space, right? And so this band here, that black band, is the pressure wave, or the compression wave. And then the next one, remember, was rarefaction, right?
Mm-hmm.
Which is low density, low pressure. And then it just alternates back and forth. And this one over here, of course, would be, again, a compression wave, right?
Yeah.
So there's a little activity I do with my students where I tell them to stand in the hallway. I'm going to draw a little picture here, just so you get a sense of what I have them do. So what I have them do is I have a student stand with arms down like this, shoulder to shoulder with each other.
Mm-hmm.
Okay, and this extends all the way down. So I have as many kids in the class do this. They're all touching shoulder to shoulder.
Okay.
When one of the people on the end, I tell them to move to the right abruptly and bump into the next person next to you. That happens pretty quickly because the distance between their shoulders is very small, right?
Yeah.
So as soon as the guy on the far left jerks to the right, bumps into the second person. Well, what does the second person then do? Bumps into the next person, bumps into the next person, and the so-called wave propagates, and you can see the people moving, but they all don't move to the right at once, right? There's a certain amount of time it takes for this movement to get from the left side of the line all to the right side of the line. But you'll ultimately see them all shift to the right and then move back to their original spot. And the next person shift to the right, move back to their original spot. That little ripple happens quite quickly because they're very close to each other. And that's my model for them to understand why the speed of sound through a solid material is very, very fast. Like the speed of sound through water is extremely fast compared to the speed of sound through air. Because water is a solid, all of those atoms are very, very, very close to each other. Each of the water atoms, when you're underwater, each water molecule is very, very close to the next nearby water molecule. Just like these students are very, very close together, so when they get bumped, they don't have to cover any distance. You know, when they look to their next atom in this drawing I just made for you, the next atom is the shoulder right next to them. They only have to move a fraction of an inch and they already bump into the next atom, right?
Yeah, yeah.
So this, again, is their model for seeing why that ripple goes very rapidly down the hallway, because they're all so close together. I then tell them to do the same exact, but in the next time, in the next instance of them doing this, I have somebody, stand like here, and then the next person is over here, and then the next person is over here, and now there's a empty space between them, right?
Yeah.
And so I do the same thing with all the students with 5 or 6, 7 feet between each student, and I say, okay, person on the left, you're going to start this again, and I'm going to say go, but then you can't, sprint over to the next person, but you casually move, walk at a walking pace and then bump into the next guy, and then move at a walking pace and then bump into the next guy, and same idea. And of course, we time it so I can illustrate the idea that I time how long it takes the first person to move to finally that ripple to eventually reach the person that's on the end of the line, right?
Yeah.
In the first case, when they're really tightly packed, that whole thing can go, I don't know, take 3 or 4 seconds. And again, when I do this the second time, I'm careful I remove people from the line when I do this one, because when they spread out, they'd ultimately be a much larger distance. And I didn't want them to think that the more time that it takes to get to the end is because their line is longer. So I remove people from this second example that I do with them, so that the distance between the first person and the very last person is the same in both cases. Does that make sense? Does that make sense?
Yeah.
And so when they do this, it could take 12 seconds before that wave eventually hits the end person. And that's the distance between left side and far right side, again, is the same distance as the distance between left side and far right side compared to when they were tightly packed. And so I'm showing them that this is more the idea for gas. Gases have great distances between them. And so when you try to make a sound wave, and that wave is kind of like these people. A certain air molecule in the wave has to move this, like, look at this person right here. He has to move over and bump into him. And then what does he do after he bumps into him? He returns back to his initial position. And what does the second person do? Move over and bump into this person, and then comes back to the original. And then every time they move over and bump, they return back to their original position. Air molecules do that exact same thing. And so in gases, granted, it's fast. It's 750 miles per hour, give or take, the speed of sound in a gas. But that's comparatively very, very slow when you're looking at the speed of sound in water, which is over 2,000 miles per hour, or 1,500 miles per hour, something like that. It's like twice as fast in water. So does that make sense as to why?
Yes, it does. Yeah.
Okay, because that's an important part of this next question, which they've asked. Well, there's actually a whole other part to this, so I'm actually going to erase this. The speed of sound. You should know that in all cases, speed of sound is fastest, is greater in any solid medium than speed of sound in a gas. And it also turns out that if I go over to my internet, get this to work. Jeez. Hoping to find charts, so just give me 1 second. Normally easy to find a chart. Is that the one I just picked? No. Jeez, okay, so I want to give me 1 more second. I wanted you to see this list, list of speed of sound. Come on, there we go. Let's try this one. There we go. So here's, can you see this list here?
Yeah.
So notice that the velocity is over here. I'm not even entirely certain what, I guess it tells us right there, velocity of longitudinal wave. So V, I'm not sure what EXT stands for. But I was just trying to show you a general idea. If you looked at, you know, like rubber, the speed, this second column is showing that the speed of sound in rubber is 1,600 meters per second. If you looked at nylon, 2,600 meters per second. If you looked at now steel or titanium, 6,000 meters per second. Steel, 6,000 meters per second. So I'm pointing out that the speed of sound is very much different in different, as it passes through different materials. We're referring to solids right now, right?
Yeah, yeah.
Copper, 5,000 meters per second. I was hoping they'd have diamond on here. So generally speaking, generally speaking, when you're talking about the speed of sound through solids, when the solid is the most dense, then those atoms are the closest together, like the people that were standing side by side, right?
Yeah.
In really dense matter and material, very small distances between atoms, that ripple goes very, very rapidly. So one of the fastest speeds of sound is the speed of sound in diamond, because it's so hard and so dense, because those atoms are so close.
Okay.
Okay. The other thing is, the other thing that the speed of sound depends on is elasticity.
Mm-hmm.
So, speed of sound also depends on temperature and elasticity. So elasticity is how springy, if I could use the word springy, the medium is. So springy, my word springy would refer to how rapidly it returns to its original position.
Original position?
Yep, exactly. After it is deformed. So, for example, typical rubber balls, like a super ball,
Yeah.
those are extremely elastic. So when you squish them, when you hold them in your hand and you press with your thumbs to squish them in, when you release your thumb, it almost instantly springs back to its original shape, right?
Yeah.
So that's considered extremely elastic. The exact opposite of that would be like memory foam, a memory foam pillow. True memory foam. Have you ever pressed a true memory foam mattress or pillow?
Yeah.
Right. Right. You press it in, and then you see it slowly returns to its original shape. That would be very, very low elasticity. Okay. And so more elasticity, when the material is more elastic. Oops. Sorry. Faster sound.
Say that again?
So more elasticity corresponds to faster sound waves.
But there's technically not that much elasticity in a diamond, though. So how would that?
Right. So it depends on two different factors. That's the tricky. It doesn't only. So there's really another list here. I mean, another part to this list, which was density.
Okay.
So this is really 1. This is really 2, and this is really 3. So you can technically have something that's not elastic like diamond, but extremely dense, and the speed of sound can be very, very rapid due to the density factor, not due to the elasticity factor. On the other hand, you can have another material that's extremely elastic, but not very dense at all, and it can still travel quite quickly, even not because it's really dense, but because of its elasticity. So there's multiple factors that can result in a very fast-moving sound wave, and some materials get that fast-moving sound wave for reasons that are different than other materials. I don't know if that makes sense. It's kind of there's a lot of things in physics that depend just on one thing, but this is one of those things, the speed of sound, that depends on multiple things. And if a certain material happens to have a high value in any one of those things, it can have a fast-moving sound wave through it, even though it's not high in those other things.
I got it.
Okay. And the other point that I want to make is that temperature and elasticity are related to each other. So these are often tied together. So what I mean is by that is think of a piece of gum. When you chew a piece of gum, is a piece of gum typically quite elastic?
Yeah.
Yes, extremely elastic. Now, have you ever been chewing a piece of gum and then drank ice cold water?
Yeah, and it would harden in that way.
So as soon as the temperature drops for that piece of gum, what happens to its elasticity?
It became more rigid.
More rigid, right? So
yeah.
On the other hand, have you ever been chewing gum and then drank a cup of hot water while the gum was in your mouth?
Not necessarily, or would it be more elastic?
Yeah, or even like hot coffee. Have you ever drank a sip of coffee with a piece of gum in your mouth?
No.
It becomes extremely loose and extremely elastic, like way more than it normally is when it's just normal gum. It becomes almost mushy, like a really mushy, very easy. I'm just pointing out that this is why it's confusing, because for number 4, your first question, they're referring to the speed of sound and how the speed of sound relates to temperature. Okay, and so let me ask a quick question to you: do you think which one do you think is more dense? Air when it's cold or air when it's hot?
Air when it's hot.
Okay, so let's go to this picture over here. I'm going to draw a picture, another picture. So right here. So cold air atoms will be very close together, like this. Where hot air, they're like this. So based on my picture, which one is showing a greater density for those little circles represent the air molecules.
So the cold air would be more dense.
Yeah, exactly. Yep. Is that what you said?
Yeah, I said hot air.
Okay. Yep. So this one's more dense. And so most students say, "Wait a minute, Mr. Kurtizak, we just did this thing in the hallway where we all stood next to each other, and you were telling us that when things were really close together, that things will move fast." And I have to say, well, that actual activity we do is just a model of solids. That was a model for solid materials. And so you can't apply that same model to gases, because when they do, they get the opposite answer in their head and then they get confused. So when you're dealing with air, students look at this picture that I just have drawn for you and would immediately assume that sound must travel faster through cold air because the cold air is closer together, right?
Yeah.
Now remember, the speed of sound depends on multiple factors, right?
Yeah.
So although that rationalization that the students are using is true, it's not that it's wrong. It's true that with cold air, the atoms are closer together, and if that was the only factor at play, the speed of sound would be really fast in cold air. But it's not the only factor at play. The other factor at play is the elasticity of the material. And it turns out that air, the air we breathe, is like gum. When it gets warm, it becomes extremely elastic. It springs back. When you push on it, it springs back to its original position very, very rapidly. So there's those two factors. So true, even though cold air is close together, that should help the speed of sound be very, very fast. It turns out that the elasticity factor is much stronger of a factor than how far apart the atoms are. And because it's more elastic when it's very warm, the speed of sound is actually fastest when it's warm. Because elasticity is the dominant factor. It dominates the other factor of how close the atoms are together.
I don't understand.
Okay, and so for that reason, temperature, as temperature rises in general outside, sound will travel faster. Because remember I was pointing out before I erase this, which I'll do in a minute, that more on the board, more elasticity creates faster sound waves.
Yeah.
So that's the reason. And it gets really warm, the air. You can think of gum if you ever forget which one it is. Think of gum and say, okay, when gum is warm, it becomes more elastic. Air is the same. And so more elasticity produces a greater springiness effect and allows you to travel through it much more rapidly.
Gotcha.
Okay, and so there ends up being an equation, not surprisingly, for the speed of sound in air. And it is, let's see, it's 310 plus 0.6 times T, and this is in degrees Celsius. Oh, it's not it's not 310, it's 311. No, I'm sorry, I'm totally doing that wrong. It's 331, because that wouldn't produce the right answer. So it's 331. Why is this not working? That's the correct one. 331 meters per second plus an extra 0.6 meters per second for every 1 degree Celsius that you add to the temperature of the air. So let me erase this so I can build on this so it makes sense.
All right.
So let's say the temperature of the air is 0 degrees Celsius. It's freezing.
Okay.
0 degrees Celsius. Then the velocity of the sound in that air would be 331 meters per second plus 0.6 times what temperature would we stick in? 0. And so the velocity of sound in that temperature should be 331 meters per second. What if the temperature was 1 degree Celsius?
It would be so it would be 331.6.
Yep. Meters per second. And then let's just do one more just for the heck of it. Let's say it was, I'm going to erase this over here. So one more just to make sure you get the idea that the velocity, oh, sorry. So one more is, let's say it was 2 degrees Celsius.
Okay.
Then the velocity would be 331 plus 0.6 times 2. And so now you're looking at 331 plus an additional 1.2. So you're at 332.2, right? And so for my point of doing this 3 times is for you to see. This was our baseline velocity of sound when it's freezing, 0 degrees. Then when the temperature goes up by 1 degree, it gained an additional 0.6 meters per second, right?
Yeah.
Then when you go up by another degree, it gains another 0.6. You go from 331.6 up to 332.2. So does that make sense?
Yeah.
You'll gain an additional 0.6 meters per second of speed for every 1 degree Celsius warmer that it gets.
Okay.
Let me erase this piece. So do you have a guess? I'm going to have you take a guess here as to what this graph would look like if we made a graph of velocity of sound versus temperature of the air.
It'd be a diagonal lineup.
Yep, good. What would the y-intercept be?
0.
Would it be 0?
No, 0.6.
So look back at this. Here it is. well, let me draw it right here. Velocity of sound equals 331 plus 0.6 times t. So think, what is the form in a math class for a linear graph? You were right by saying up and to the right. That's correct. It's a diagonal. So what is the standard form for a linear data set? What is the equation that models any linear graph?
Y equals mx plus v.
Yep, good. So this would be our y, because it's on our y-axis, right? What would our x be?
0.6.
So out of this here, x would actually be, because what's on our x-axis?
Oh, air, so x would be t.
Yeah.
Mm-hmm.
So what would the 0.6 be?
That would be the m. It changes.
Yep, and then therefore what would 331 be?
B.
B. Very good. Does that make sense?
Yeah.
It's just now backwards, b plus mx versus mx plus b, but that doesn't matter the order, right? So what would the y-intercept be? It would be right here, and what value would it be on the graph?
It would be 331.
Yep, good. 331. So that would be colored in as a data point, and then it would slope which way?
It would slope diagonal to the right.
Yep, exactly. Up like this. And then if you took any two data points, like this one and this one, and decided to get a slope by doing rise over run, what number would you get?
You're going to get a slope of 1.
That, look back at the equation.
So a slope of 0.6.
Very good, yep. 0.6 will be your slope. So that means for every 1 degree Celsius that you're going to the right, how much are you going to go up?
0.6.
Yep. 0.2 degrees Celsius, right?
Yeah.
Does that make sense?
Yeah.
Okay. And so now let's look back at the problem. So one for sure thing you need to know, the speed of sound is fastest on hot days. Always faster. The speed of sound is always faster when the day is warm, and then if it's a cold day, sound will travel more slowly. That you definitely need to know. And let me go back to now trying to read this question and see what it said. Number 4 says, on a warm summer day, which is 31 degrees Celsius, it takes 4.8 seconds for an echo to return from a cliff across a lake. On a winter day, it takes 5.2 seconds. What is the temperature on the winter day? I think I got one. Distances are the same, velocities. I'd have to think about that one for a minute. So let me point out, when a sound is moving through air, is it accelerating or is it moving at a constant speed?
The speed?
Yep, exactly. So I don't know the answer to this one right off the bat, but let's see if we can work it out. What is the equation for constant speed motion?
Equation for constant speed motion.
Yeah, something that relates how far you're going to travel, distance, to how fast you're traveling, velocity, and t, how long you've been driving for, how long you've been traveling for. What equation would relate all three of those variables together for constant speed motion? So think miles per hour. You know that velocity is it could be reported in miles per hour, right? So miles per hour, what unit is miles out of these three?
Say that again, Eddie.
What unit is miles out of D, V, or T?
D.
D. So we'll put D here. What unit is hours out of D, V, or T?
Time. T.
Time. So we get velocity must be distance over time.
Okay.
Right?
So next.
And so let me erase some of this. Because this is definitely going to require two equations, but I'm assuming that this is going to be one of the ones we have to use. And they say that you are yelling like this, and then the wave travels over to some wall and then echoes and comes back, right?
Yeah.
And they're saying that the time echo to return originally is 4.8 seconds. It's 31 degrees Celsius. And then when it's done again on a colder day, does it make sense that the time is longer?
No.
5.2 seconds for it to return when it just says winter day. Because remember, when it's colder, when the air is colder, does the sound wave move faster or slower?
It's faster.
When it's colder.
Oh, no.
Remember, look at your graph on the top left of the screen.
Oh, yeah. It's slower.
Yeah, so when it's colder, the air sound wave moves slower. So does that make sense as to why it takes a little extra time, 5.2 seconds, compared to the 4.8?
Yeah.
Okay. So let's see here. Let me come over here. Erase. Not 100% to be honest how we're doing this one. I might have to puzzle on this one for a minute. The velocity of sound will be the distance, will really be 2 times the distance. Or you could just leave it as distance, I suppose. Just calling the distance all the way there and all the way back, we'll just call that total distance d, divided by how long it takes. So, in fact, while I'm thinking, I know for sure you're going to have to use this information, 4.8 seconds, 31 degrees. Could you work out, using our formula that we already had on the top, what the speed of the sound is if the temperature is 31 degrees?
Yes.
So why don't you work on that while I'm thinking? Because that you're going to have to do, I'm certain of that.
You said 31 degrees, right?
Yeah. Oh, I just figured it out. Yeah, that's a tricky question. Yes, it's 31 degrees. That's warm, by the way. That's like normal room temperature is.
This is measured in Celsius, not Fahrenheit.
Yeah, exactly. I wanted you to make sure you recognize that. That's 31 degrees Celsius is over. I don't know. It's probably, I'm guessing, like 75 degrees Fahrenheit. So that's a warm day.
Yeah.
So use the 31 degrees and stick it into that formula that's on the top of the screen to work out what the velocity of the sound wave is on that 31 degree day.
Okay.
All right.
We got 349.60.
Okay. So I'm going to write it out here if you don't mind. Velocity of sound will be 331 plus 0.6 extra degrees for every 1 degree, and we got 31 of them. So it'll be 331 plus, where's my calculator? 0.6 times 31. So it's an extra 18 at your, oh, I didn't mean degrees, an extra 18.6 meters per second that you're getting for it being that warm above freezing. So that would be 19 would have been an even 350, so it'd be 349.6. Is that what you got?
Yeah.
Okay. So this is the velocity of sound on 31 degree Celsius day, right?
Yeah.
Now remember, sorry. What is the formula again for velocity, distance, and time? Do you remember it? I erased it. So
V equals D over time.
Yep.
Distance over time.
Yes. So do you know the velocity of the sound wave now?
Yes.
Yes. So check. Do you know how many seconds it took to travel that distance?
No.
So go back and read number 4 if you don't mind.
Oh, 5.2.
So we're working on the first one, the 31 degree day.
4.8.
Yep, 4.8. So can I point out that we are actually going to have to think about 4.8 seconds is how long it takes the sound wave to go all the way over off and hit the wall and then come all the way back. So what can we do to focus on just one trip from where he yells to the wall? What should we do to
Divide by 2.
Yeah, exactly. So the time is not going to be 4.8. It'll be
It's going to be 2.4.
Yep. So that makes sense, right?
Yep.
And now we have T. Can you solve for D?
Yes.
So can you try it?
I got 839.4.
Sorry, just give me 1 second. Okay, so 349.6 times 2.4, right?
Yeah.
Yep. Oh, did I ever hit record?
Yes, I believe you did.
Oh, I did. Good. Okay. So we're getting 349.6 times 2.4. So what number did you get for an answer?
139.04.
Yep. Okay. We're good on that. So the distance is 839 0.04 meters, right? So now we know the distance to the wall, just knowing how fast the sound was moving and how long it took to go that distance, right? So now, can we technically use the same formula, distance equals velocity times time? Do we know the distance? Yes.
Yes.
Do we know the new time on the winter day?
Yeah.
Yes. Can we solve for what the velocity must be on that day?
Yeah.
Do you want to give it a try?
Yeah.
That should be... And should it be a velocity? Because remember, the velocity of sound on the warm day came out as about 350 meters per second. Should your answer that you calculate be more than 350, still 350, or less than 350 on this cold day?
Less than 350.
Right. So in your head, you already have an idea, and then let's see if your answer supports the idea.
We don't have a degree, so how would we plug it into what then?
We don't have to anymore. We can just use distance equals velocity times time.
Okay.
You see this one again? And do you have the distance now? 839.04 would go in for D.
Mm-hmm.
And what will we stick in for T?
Well, 5.2.
Be careful.
Or half of 5.2.
Yep. 2.6 seconds, right?
2.6, yeah.
Yep. And now your only unknown will be V, and that's what they've asked for. Oh, I'm sorry, that's not what they've asked for. So you still have to do this part. So you have to get what the velocity is, and then we'll finish it off in the...
Yeah, and then get the degree.
Yeah, I didn't recognize. They were actually said, what is the temperature on this day? So once you have that velocity, it'll go, and your unknown will be the capital T temperature.
Yeah.
So you don't have to finish it now. You can if you want, but does that make sense?
Yeah, we can finish it.
Yeah, okay, I don't mind waiting. On the next one, number 8. So before we can do the next one, I have to teach you some more stuff. Oop.
Alright, so some velocity I got 322.71 meters per second.
1 second, divided by 2.6. 839.04 divided by 2.6. I'm getting, what did you get?
322.71.
Yep. So is it in fact less than the 350 that it was before?
Yeah.
Yeah, because it's what? Cold or hot?
Because it's cold.
Because it's cold. Yep, you got it. Now this has to go where? Into the top formula, right?
Yeah.
Which is 331 plus 0.6 T. So we'll take 322 and stick it in for V, right?
Mm-hmm.
And then you'll solve for T.
How would I solve for T then?
It's okay, I can help you. So are you looking at the board on the bottom?
Yeah.
So we'll be using this now.
Mm-hmm.
And let me erase this section. So now in for velocity is going to be the velocity that you just calculated, 322.71, right?
Yeah.
That part is the v that you see right here, right?
Yeah.
And then equals 331 plus 0.6 t. And so now we just need to solve for t. So what would we do?
Subtract
Yep.
51.
Yep.
And then divide 0.6.
Yep, you got it. So that gives me negative 8.29 divided by 0.6.
I got negative 13.82.
Yep. Yeah, you have it right. I didn't round up properly. Yep, negative 13.82 degrees Celsius. And remember, when it was freezing, when it was a freezing temperature, what would the temperature have been? If it was 0 degrees Celsius, which is freezing.
The temperature would have been.
If you look back at that formula, what would you get for that velocity of sound wave if it was 0 degrees Celsius?
331.6.
331. And what is the velocity of the wave now?
It is 322.
Right. So does that make sense why it's negative?
Yeah.
Yep. Good. That's it.
Right?
All right. I'm going to erase the whole thing. Is that all right?
Yeah. Okay.
Okay. So the next idea is an important idea. It's a whole new idea I have to show you. I think. Let me just double check. We're moving on to number 8. So this new idea is called intensity of sound, decibels, which is sound level, so this is really the topic of sound energy, the idea that there's energy in sound waves.
Mm-hmm.
So give me 1 second. Okay, so have you heard of the word decibels before?
Yes.
So is a measure of how loud a sound is. Well, it's not really how loud. That can be confusing, so I don't want to word it that way. The energy in a sound wave. And it's measured in decibels. And the shorthand for decibels is D, lowercase d, capital B. And so this is a scale that starts out at 0 decibels, and 0 decibels is the minimum, the faintest sound that could be detected by a human ear. So the quietest, faintest sound imaginable someone could potentially hear, and how they... What's that? Is 0 decibels. That's how they decided to define the 0 mark. The quietest possible sound that a human can hear. It doesn't mean that if there was some value under that, that those sound waves aren't moving. It just means they are moving, but they're so quiet, there's so little energy in them that they're not sufficient to make your eardrum move, so you wouldn't detect that sound.
Okay.
So this scale goes from 0 decibels up to some, it can really go up to any value. It really can go up to infinity, but practically speaking, it goes up to, I think, about 120 or 140. Let me actually check the book. Where's that book? I think like jackhammer is like 120 decibels, like a Boeing jet. You know, when if you're standing very close to the jet on the airport, and that jet was running, you're looking at like 130 or 140 decibels. If you have a very loud concert, like right next to the speaker, maybe 150 decibels. So, we measure in our practical world is about 150. But it doesn't mean that you can't have a sound wave that is more than that. There's no limit. You can, in theory, it could go up to any number. But I don't really have to cross-reference myself. You could always look in your book. There's lists that show typical sounds that you'd see in our world and what the decibel levels are for them to give you a sense. But just know, I'm pretty sure it's somewhere around 150 decibels for like a loud concert. Okay?
Yeah.
So it turns out, actually, before I tell you this, are you familiar at all with earthquakes in terms of what's called the Richter scale?
Yeah.
So it turns out like Richter scale goes from 0. I think it also can go up to any number, but practically speaking, I don't know if there's ever been an earthquake that's measured over 10. I'm pretty sure the largest earthquake ever measured was under the number 10. So the Richter scale and I'm telling you this because there's a similarity between how they measure how much energy is in an earthquake, as a similarity with that, and how they measure how much energy is in a sound wave. So Richter scale, generally speaking, goes 0 to 10. Now, let's say you had, earthquake 1 is a 2.0 on the Richter scale, and earthquake 2 is a 3.0 on the Richter scale. Do you have maybe you've learned this, maybe you're not, you haven't. If you haven't, no big deal. But I'm going to let you guess it. How much more energy would be in earthquake 2, based on what I just wrote, compared to how much energy is in earthquake 1?
It would be, sure.
It's okay. So it turns out that, what is the difference between the Richter scale readings? 3 minus 2 gives us 1. So for every 1 unit, it's a factor of 10. So this is actually 10 times stronger. I shouldn't say stronger. That's poor language. It's 10 times more energy. So there's, in my example that I'm doing here, there's 10 times more energy in the 3.0 Richter scale reading than there is in the 2.0 Richter scale reading. Now, watch this closely because this is very important and very much sound. If the second earthquake was not a 3.0 on the Richter scale, but it was a 4.0 on the Richter scale, what is the difference between those two now?
20 times. Yeah, 20 times more energy.
So I know it looks like it's 20, so I'm sorry for that. That actually just is 2.0 and 4.0.
Is that the 20?
It's not a 20. That's supposed to be a 0.0, like 2.0. I'll erase it. Hold on a minute.
Oh, I see 20 because like you said like the difference between.
Oh, okay. Oh, okay. I didn't follow. Okay, so what I was saying was, what is the difference between the Richter scale readings 4 and 2?
4 and 2.
What's the difference?
The difference of 2.
Right, the difference is 2. So it turns out that it's not 10 times more energy. Since it's a difference of 2, it's 10 squared.
Oh, 10 squared?
Yeah. So now it's now 10 squared, which is 100 times more energy in a 4.0 Richter scale earthquake compared to a 2.0 Richter scale earthquake. We're going to do one more of these, if you don't mind.
Okay.
If the second earthquake was now not 4.0 on the Richter scale, but 5.0 on the Richter scale, the other one was 2.0 on the Richter scale, what is the difference between those two readings now? What is the difference between the Richter scale readings?
10 cubed.
Yep. So the difference is 3, and therefore it's 10 cubed, which is
1,000.
1,000. Yep. So now you get 3, and so when you find the difference, that ends up being the power that you raise 10 to. So this is a 10 cubed difference, which is 1,000 times more energy in a 5.0 Richter scale reading earthquake compared to a 2.0 Richter scale reading earthquake. Does that make sense?
Yeah.
It's 1,000 times more energy. So that idea is called a logarithmic scale. A logarithmic scale. A logarithmic scale works on powers of 10 to define the value of something.
Mm-hmm.
So let me write that down because it's definitely, this whole idea is how, they use the same system to define how loud sound is.
Okay.
Or say how much energy is in a sound wave. So, sorry, give me a second. So actually, can I erase that part that I just did for you?
Yeah.
Okay, so erase this whole bottom. And just note a logarithmic scale and you know what I mean by powers of 10, right? Like 10 squared, 10 cubed, 10 to the fourth.
Yeah.
So a logarithmic scale utilizes powers of 10 to define the value of something. So the Richter scale is a logarithmic scale. So it turns out that the decibel scale is very similar. So back to sound. So if you have a 30 decibel sound, so that's going to be sound 1. And then sound 2 is 40 decibels. How much more energy in sound 2?
Um, 7 times more energy.
Yep, very good. So you actually figured that out without me telling you. So remember before with the Richter scale, it was like a 3.0 versus a 2.0?
Yeah.
And the difference was just the number 1. That corresponded to a factor of 10 times more energy. If the difference was the number 2, then that was 10 squared times more energy. When they're doing sound waves and sound energy, you take the decibels and you subtract them. For every 10 units is a factor of 10 times more energy. So that's 1 factor of 10 more, or I should say times more energy. Okay? So let's do one more example. Let's say sound number 2 is not 40 decibels, but now sound 2 is 50 decibels. Same question. How much more energy? How much more energy is in sound 2?
20.
So you do the difference, which is 50 minus 30, and you do get number 20. So the difference between those is 20 decibels. But when you're interested in how much more energy does that correspond to, for every 10 that you can fit into that 20 decibels, that's 1 factor of 10. So how many 10s go in? How many 10s go into 20? 2. That is 10 squared. 100 times more energy. Let's do one more. Let's say it was 60 decibel. You always start by subtracting. After you subtract, what number do you get? 30. Then you take 30 and divide it by 10.
Get 3.
Yep. 30 divided by 10 is 3. So then you do 10 to the third, which is what? 1,000 times more energy in the 60 decibel sound than the 30 decibel sound. Does that make sense?
Yeah.
Want to try one more on your own?
Yeah.
How about if it was a 20 decibel sound being compared to a 70 decibel sound? How much more energy would be in the 70 decibel sound than the 20 decibel sound?
50, so it's 50 from 10 to the 5th, and that's what?
You have it. Yep.
No, 10,000.
So, yep, you had it close.
100,000.
Yep, 100,000, yep. So 100,000 times more energy in the 70 decibel sound than there is in a 20 decibel sound.
Mm-hmm.
All right? So you get the general idea. There's a formula for it, and I'm going to give you the formula. I wanted you just to get a sense of this idea of a logarithmic scale.
Okay.
All right, so let me jot that down for you now. Can I erase this?
Yeah.
All right, let me look back at the question and just... Okay, so before I do that, so now the formula for this is that the decibel rating is equal to 10 times the log. Oh, I can't even, well, I'll write it down. I realize there's one more thing I have to show you.
Okay.
I stands for intensity.
Say that again?
So the symbol I stands for what's called intensity. And I don't know if you have ever learned in this course yet what power means. Did you learn about power?
Power, like exponents, or?
Power in terms of
Power, like what's that?
power in terms of energy.
Yeah.
power is measured in watts, and watts is how much energy joules per second, per 1 second. So, for example, if you have a 10 watt light bulb uses 10 joules of energy per 1 second of usage. If you have a 50 watt light bulb, it uses 50 joules of energy per 1 second of usage. Okay, that's called power. And power generally is this is really what I'm referring to right here. This is a rate. It's the rate, which is, it's an energy rate, which is how quickly energy is being used. So in my example, the 50 watt light bulb uses energy at a faster rate because it uses 50 joules of energy every 1 second compared to a 10 watt light bulb, which only uses 10 joules of energy per second. Does that make sense?
Yeah.
Okay. So power is a rate. It's an energy rate, how rapidly energy is being used. I had to tell you that because the units for intensity is the amount of watts per 1 square meter that a sound wave is hitting. So let's say you had a board, and the sound wave is coming along like this, and it's going to run into your board. If your board is physically 1 meter this way by 1 meter this way, then what would the area of that board be? A board that's 1 meter by 1 meter, what would the area be? It would be 1 times 1, which is...
1 times 1.
It's okay. Yeah, my 1 sometimes looks like 2. So a 1 by 1 board would be a square that's 1 meter in length by 1 meter in width, and the area would be 1 square meter, right?
Yeah.
Okay. And so this picture that I'm showing here is my sound wave picture that's moving towards that board, right?
Yeah.
If there is, the energy in that wave is 50 watts. So let's say there's 50 watts of energy in that wave that's moving towards the board, then what would the intensity be if you come back up here? It would be 50. Yep, it would be 50 watts per 1 square meter because all of that 50 watts of energy is going to hit the 1 square meter board, right?
Yeah.
And so the intensity would just be written typically as 50 W/m squared. W stands for watts. So it's 50 watts per 1 square meter, right?
Yeah.
So intensity is a measure of how much energy per second is running into a certain amount of surface area. So let me write. Intensity is kind of a complex unit because there's lots of other units embedded in it.
Mm-hmm.
Watts is already sometimes complex. You have to remember watts is, again, not it's energy per second. It's a rate. Again, watts is how many joules of energy per second are being transferred to something else.
Yeah.
So intensity is watts, which is energy per second. And how much of that energy is running into a certain amount of something. So like your eardrum has a very small surface area, right?
Yeah.
And so when a sound wave hits it, that energy is being placed onto a very small surface area drum. And so intensity, this new thing that I'm trying to teach you called intensity, this thing called sound intensity, doesn't depend just on how much energy is in the wave. It also depends on how big is the detector.
Okay.
Right? If you have a dog ear, dogs can hear quite well because if you lift up their ear, might have floppy ears. If you lift up their ear, you'll see that they have a much larger ear section than we do, right?
Yeah.
And a much larger eardrum. So why is it that they are so much better at hearing? Because the physical surface area of their sensor, called their ear, is much larger, right?
Yeah.
And so my point to you is that the intensity of a sound, when you have a certain sensor, it could be your ear, it could be a microphone, it could be anything really. The intensity that that sensor feels depends on how much energy is moving towards it, as well as how much surface area the sensor has to collect that energy. Okay? So intensity is how much energy per 1 second. Let me erase some of this if I could. In fact, I'm going to just start over. I'm going to erase this. So intensity is how much energy per 1 second is being, actually I'm going to erase all of it. So I backed up. I was going to show you the equation with the log in it. Let's wait on that. I have to realize there's a couple extra things I have to build upon, and then I'll show it to you. So there's a formula that's I is equal to power divided by area. Because remember, I had just shown you that the units for intensity were watts, which is power, divided by square meters, which is area, right? The units for I are watts per square meter. So the intensity of a sound is the power in watts, remembering that watts is joules per second. This is energy, joules of sound energy per 1 second, divided by the area of the surface the sound wave runs into. So I equals P over A. So if you have a certain amount of energy, for example, let's say when I scream, if I scream as loud as I can, I emit a certain amount of energy into the airwaves, into the sound, right? Or into the sound waves, and I emit that energy into the air, right? If you were to just hear my sound with your normal sized ear, would the area and the denominator be big for your ear, do you think?
No.
No, it's tiny, right? And so you'd end up having a certain amount of energy going into your ear. And that area affects the intensity in the sense that when power and energy gets distributed over larger areas, what happens to the intensity? It kind of gets spread out, almost like a wave. If you drop like a water wave, if you drop a pebble into a pond that's nice and flat, then it starts off with a little ripple, and the size of that circle is kind of small, right?
Yeah.
And that if you went around that circle, the circle is going around the central spot where you dropped the rock. and you see the if you're looking down, you see a circle gets bigger and bigger and bigger, right?
Yeah.
The wave, as you go around that whole circle, has a certain amount of energy. But as the circle gets bigger and bigger and bigger, what's happening to the total energy of the wave? Is at any given point, if you were a surfer, what would be happening to the height of that wave as it gets larger and larger and larger and larger and continues spreading out further and further and further? What would happen to the height of the wave?
It would decrease.
Decrease. And therefore, if eventually you're sitting way away from it, that little tiny wave eventually hits you, does it impart a lot of energy to your body?
No.
No. But what if you were sitting on your little surfboard right next to where someone drops the rock? Would that impart more energy to you when the wave hits you, if you're close to where it was dropped?
Yeah.
Yes. And so the idea is when the circle wave gets larger and larger and larger, think of that as A, the area and the denominator. As it gets bigger and bigger and bigger, what does that do to the intensity of the effect on the surfer?
It increases.
As area increases, what happens to the intensity?
No. Decrease.
Decreases, exactly. So I'm just trying to point out that when things get spread out in space, when they eventually run into something, if they've been spreading out for a long, 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 long time, then that area is being spread out in 3 dimensions, in X, Y, Z dimensions. And if it's been expanding and expanding and expanding for a long time, then when it eventually runs into your ear, it's not going to impart that much energy to your ear. Okay. However, if you're really close to the source and it hasn't been expanding that long, more energy, area would be smaller, think of it as that way, I would be larger, it would seem louder to you, right?
Yeah.
Right, okay. So that's the idea of intensity. It relates to power and area. So definitely jot that one down because you need that. In fact, just a quick comment to you, you will need that for number, where is it? So I remember noticing number 14. Is it number 14? Yeah, you'll need this, what I just wrote for number 14.
Okay.
Now, let's finally get to the other one. That the loudness of a sound in decibels is equal to 10 times the log of the intensity of some sound that you're, so this is decibels of a sound. This is the intensity of that sound. This intensity is the intensity of the sound wave that you're interested in finding the decibel level of. Okay? Divided by what's called I naught. I naught, I0 is the minimum sound humans can hear. Remember I said that that minimum sound corresponds to 0 decibels?
Yeah.
Well, 0 decibels actually turns out to correspond to 10 to the minus 12 watts per square meter. That's the minimum intensity that a human can hear. The minimum intensity that a human can hear. And it's always in all calculations. It always goes in the denominator. So whenever you're trying to find out what the decibel level is of a certain sound, let's say a jackhammer,
Yeah.
you always use in the denominator the number 10 to the minus 12, which references the minimum sound that a human ear can hear. Because to determine how loud the sound of a jackhammer is, you need to know with reference to what? They always want to reference the quietest possible sound that we can hear at 0 decibels, which turns out to have an intensity of 10 to the minus 12 watts per square meter. So think of it as just like a constant. It's always that number in this equation, 10 to the minus 12, and it always goes in the denominator. And so let me do an example for you. In fact, why don't we try one of the ones that are your problems? I'll try to do that as the example. Let's see, number 8 and 13. Okay, so can you look at number 8? Because I'm going to show you how to use this now. You there, Jeremiah? Okay.
Yeah.
So it says, what is the intensity of a sound at the pain level of 120 decibels?
The pain level?
It turns out that if you were hearing a sound that was 120 decibels, there would be pain in your ear. That's loud. That's really loud.
Okay.
That would damage your hearing. You know? Yeah, like I said, if you were at like a huge rock concert with the massive speakers intended to be really loud to get to all the people, and you put your ear right next to that speaker, that would be like 150. That would be like, yeah, blow out your eardrum, and that would be like 150 decibels. So at 120 decibels, I think I'm pretty sure actually that's the mark where people start to feel pain in their ear when it's that loud.
Okay.
So they're telling us that the sound level is 120 decibels, and they just want us to calculate what is the intensity of that sound wave if it's 120 decibel sound level. And I'm going to show you how to do that, all right? So we're going to use this formula. Guess what we'll stick in for the dB, decibels?
120.
120, good. The number 10 times log for I, which is right here, divided by, and now what do we put in for I naught?
0.
It's 0 decibels, but recognize that decibels, known as sound level, let me jot that down. Decibels, which is called sound level, and intensity are not same thing. So 0 decibels is the sound level of something you can't hear. That happens to have an intensity of 10 to the minus 12 watts per square meter. So a sound of 0 decibels has an intensity of 10 to the minus 12 watts per square meter. 10 to the minus 12 is 0.00000012 times watts. That would run into a full square meter. That's an extremely small amount of energy, which is why our ear can finally not really detect it anymore.
Okay.
That's the intensity, again, the 10 to the minus 12, of a sound that's so quiet that its sound level is considered 0 decibels. So only the 0 is associated with the decibel value, the sound level. Intensity is referring to how much energy per square meter that sound wave is carrying.
Okay.
So what number will we put in on the denominator? It ends up being 10 to the minus 12. You'll always do that for all problems. It's like a constant number that is always referenced in these kinds of problems, and it's always the minimum intensity that humans can hear. You always just stick the number 10 to the minus 12 there. All right? So now let me just erase a little bit of this. Now we just have a math problem. We're going to try to solve for I, the intensity of this 120 decibel sound. So what's the first thing we can do? What should we do about this 10? Because it's 10 times the log of this ratio. We want to ultimately dismantle this whole right side and get I all by itself.
And divide it.
Divide by 10, good. Equals the log of I over I naught. 120 over 10 is the number 12, right?
Yeah.
Equals log of I over I naught. So log is base 10. A logarithm is a base 10, so like 10 squared or 10 cubed or 10 to the fifth. Logarithms are a base 10 scaling.
Yeah.
So in order to move forward from this point, all we have to do is raise, or 10 raised to the 12th power now. And when you do 10 and log, do you know what a 10 raised to the log does? It cancels.
Yeah, let's say 0.
Yep, so so it actually just is 1. So it just is the number 1. So whenever you take the number 10 and raise it to the log of something, the 10 and the log just vanish.
Okay.
They undo each other. And so all you're left with is now 10 to the 12th equals the ratio I over I naught. Which is 10 to the minus 12. So how can we now solve that one? We're solving for I.
So now you just do the inverse of that.
Yep.
So that would be 1 over 10 to the 12.
Let me just delete this part now. So we could think of just multiplying both sides by 10 to the minus 12, right?
Mm-hmm.
So what is 10 to the minus 12 divided by 10 to the minus 12? Just
0.
Just 1, the number 1.
1, 1, 1.
Right? And so now we're left with 10 to the minus 12 times 10 to the positive 12 equals the answer we've been seeking. What is 10 to the minus 12 times 10 to the positive 12? So the base is the same. 10 and 10 have the same base. So what is the rule for handling these exponents?
You add them.
Add them.
100 raised to 0.
So it would be 10 raised to the minus 12 plus 12, which is 10 raised to the 0. Anything raised to the 0 is what number?
1.
1. So our answer that we've been trying to find, I, the intensity of a 120 decibel sound wave, has how much watts per square meter? 1 watt per square meter. That seems small to me, but that's the answer. 1 watt. Does that make sense?
Yeah.
So let me erase this. Can I erase this?
Yeah.
So I'm going to show you something else to make it easier for you. So D, the decibels, this is just the equation I'm giving you, the same equation. So if you want just a formula that will allow you to solve for the intensity of a wave that has a certain decibel sound level, just like we just did, right? They said, what is the intensity of a whatever, some number, decibel wave, right? What were the steps that we had done? You put the decibels in, right, that they give you. Like in our problem, we had put the number 120 there, right?
Yeah.
And then you divide it by 10, right?
Yeah.
Then, so you have decibels divided by 10 equals log of I over I naught. And how do we get rid of the log? We say 10 raised to this value, and then 10 raised to this value, and those cancel, right?
Yeah.
And so we got 10, and then in parentheses, the decibel value that's given divided by 10 goes in the exponent, equals I over I naught. So when you solve for I, it's I naught times 10 And then up in the exponent is the decibel level that they give you divided by 10. So that's like a nice handy formula that gives the intensity of a wave, of a sound wave, that has this sound level right here, that has some dB sound level. So you would just stick the value in for dB, like 120, right?
Yeah.
And let me point out, if you had that nice handy formula right from the get-go, and we had applied the problem that you just did, look how quickly it would go. The answer we were looking for is, remember, I naught is what number? 10 to the minus 12, right?
Mm-hmm.
Times 10, raised to the, what number did they give us for the decibels? 120 divided by 10, right?
Yeah.
And then you say, oh, that's 10 to the minus 12 times 10 to the 120 divided by 10 is positive 12, and you would have quickly seen that that's 10 to the 0. The answer is 1 watts per square meter. You see?
Yeah.
So I don't think your textbook would show you that, but that's a pretty handy thing to have. It says, now let's compare it to, so why don't you try the second one if you want. Why don't you use the second part of number 8, it says, do the same thing for a 20 decibel sound. Which is considered a whisper. It says a whisper is considered a 20 decibel sound.
So now we have I equals number.
Number 8.
So now we plug in 20 into 10 times long, 10 to the, we do number 10 to the negative 20. Yeah.
So remember, why don't you just give this formula that I just wrote down for you, this new version of it, one right here,
Oh, okay.
and give that one a try. So what would be in the numerator on the exponent where it says dB divided by 10? What number would you put in now for the dB?
You hit it 20.
Yep, 20 divided by 10, and you can figure that.
That would be 2.
Yep. And so 10 squared would be what?
100.
100. And what number would you put in for I naught? Or I0, sometimes call it I0 or I naught.
10 to the negative 20.
Negative 12. So that's the constant value that
But
you love.
negative 12, that's about value.
That's okay. 10 to the minus 12. And then you just told me that the other part came out as 10 to the positive 2, or 100, right? So,
Yeah.
so what is 10 to the minus 12 times 10 to the positive 2?
Yeah, keep it 10 to the 2 or to 400.
So now you just add the exponents. Negative 12 and 2 get added.
Yeah, I know, but like, yeah, if you do out 10 to the second, it's going to go 100. You want to keep the exponent?
Yeah, keep it as the exponent because you can simplify it now. What's 10 to the minus 12 times 10 to the positive 2?
Well, it's going to be 10 to the negative 10.
You got it. And the units will be what?
I equals 10 to the.
So your answer is correct.
Watts per meter squared.
Yep, you got it. So that would be the intensity of a 20 decibel sound, which they said was a whisper.
Okay.
So if you were to try to find out how much more what's the ratio of intensity of the 120 decibel sound compared to the intensity of the whisper? What is it? Well, remember that the first intensity was 1, and then this is the 120 decibel sound, divided by 10 to the minus 10 watts per square meter, and this one was representing a whisper, right? So if you did that on a calculator, what will you get? 1 divided by 10 to the minus 10.
You get minus 10, get 1. 10 to the minus 10 is,
So your 10 to the minus 10 comes up to the top on the numerator, and what happens to the sign of the minus 10? Becomes positive, so it's 10 to the plus 10, right?
Yeah, so that's maybe
10 to the 10th times more energy in 120 decibel wave versus the 20 decibel whisper. 10 to the 10th, is that a lot? Yes. 10 to the 9th is what number?
Is that like trillion?
Yeah, exactly. No, I'm sorry. Trillion is 10 to the 12th. 10 to the 9th is...
That's billion.
Exactly. 10 to the 9th is... Let me just erase this. So 10 to the 6th is million, right? 10 cubed is 1,000. 10 to the 9th is billion. 10 to the 12th is trillion. So if we're looking at the number 10 to the 10th, that's 10 times 10 to the 9th, right? 10 times...
100 billion.
Almost. So it's 10 to the 1 times 10 to the 9th is 10 to the 10th, right? So that means it's the number 10, and then what word would you put in for this? Billion. So it's 10 billion times more energy in the 120 decibel wave compared to the 20 decibel whisper. That's a lot more. That's a lot more energy, which is why it's enough to cause pain in your ear at that point.
Oh yeah.
Okay, so we're done with number 8. Any questions on that one?
Yeah.
All right, let's move on.
It's pretty clear.
Number 14. Let's give that a try. 14. All right, I'm going to erase the board. Is that all right?
Yeah.
Okay. So number 14 says a 55 sound wave strikes an eardrum with an area, the eardrum has an area of 5.0 times 10 to the minus 5 square meters. Remembering that that's a very small amount. 2, 3, 4. That's that amount of square meters. Right?
Yeah.
Did I do that right? 1, 2, 3, 4, 5. Yeah. 5 times 10 to the... Ooh. No, that's right. Yeah, 5 times 10 to the minus 5 is a very small circle area. Right? It's tiny.
Yeah.
So let me go back here and then continue reading. It says, how much energy is received by the eardrum per second? How much energy is received by this eardrum per second? So let me remind you that energy per second what unit is that? Energy per second. What is it? Good guess. So energy per second. Well, what is the unit for energy? Joules. And then joules per second is called what you just told me, watts, right? That's the unit. And it's the unit for what quantity? The unit is, cross this out. The unit is watts, and that the unit of watts is the unit for which quantity? Power, right? So right away, we needed to identify which quantity are we going to be solving for. They've asked you to solve for how much energy is received by your eardrum per second. That's power. So we know we're going to need to have a formula that has power in it. Do you remember way back in the beginning I said this formula, I equals P over A, and that you would need it for this problem?
Yeah.
So ultimately, we're going to be solving for this one, because this is joules per second.
Okay.
This is power, right?
Yeah.
Did they give us the area of the eardrum?
No. No.
So it says a 55 decibel sound wave strikes an eardrum square meters.
Oh.
So did they give us the area?
Yeah.
Yes, they gave us the area of eardrum. You with me?
Yeah.
And we need to now find out the intensity of that sound. But all they gave us was the sound level of that sound, which is 55 decibels. How are we going to turn 55 decibels into an intensity? How do we determine the intensity if we know the sound level in decibels? What's that? I'm losing your voice. Can you maybe move it towards the phone a little more?
We have to find power.
So just think back to just about 5 minutes ago. Remember we had I equals, sorry, I didn't mean that. Yeah, I didn't mean that. My fault. What I meant was, I don't even remember now. My mind's going blank. We started with the decibels. Yeah, that's right. I equals I naught times 10 to the decibel level divided by 10. You remember that?
Mm-hmm.
So where would we stick the number 55? Because this is the formula that can turn a sound level in decibels into a value for intensity, capital I. So where would we stick the number 55?
Into the dB.
Yep. What will we stick in for I naught?
10 to the 12.
Yep.
12.
Yep. So you want to try that? Because you can now solve for the intensity that'll eventually go right here.
I get 10 to the negative 6.5.
So 10 to the minus 12 times 10 to the 55 divided by 10. So that's 10 to the minus 12 times 10 raised to the 5.5.
Yeah.
So that would be the same as 10 to the negative 6.5. So let me do that on a calculator. 10 raised to the negative 6.5. I get 3.16 times 10 to the minus 7. Is that what you got?
Okay. Yeah.
Yeah, and that would be watts per square meter. Right? So again, this formula is allowing us to take a sound that is being provided in decibels and turning it into an energy value, which is per square meter, and it comes out as that number, right?
Yeah.
Now we come back over to here on the left side of the board and say to ourselves, well, we can solve for P, because that's what they asked. How much energy is received by the eardrum per second? Remembering that energy per second is power. So P is the one we're solving for. What number will you stick in for I?
3.16.
Yep, times 10 to the minus 7. And what number will you stick in for A?
The middle area, which is
You got it. Yep.
5.0.
Yep, you want to try it?
Yeah. Eight.
Yep.
10 to the negative 11.
Yep, exactly. And so you could have just cross-multiplied this bottom equation to get power equals I times A, right? And so we would have just had the 3.16 times 10 to the minus 7 in for area, and then, I'm sorry, in for intensity, and then the area would have been 5 times 10 to the minus 5th. Yeah. So I got the same thing, 1.58 times 10 to the minus 11. What would the units be? Remember, this is power.
Watts per meter squared.
That's actually the units for intensity.
No, this is joules per second.
Yep, exactly. Or people call that what other word?
Watts.
Watts. Good job. Yep. And let me point out, in this formula, P equals IA, what were the units for I? Watts per square meter, right?
Yeah.
Times, what are the units for area? Square meter, right?
Yeah.
So what happens to the square meter and the square meter? They cancel, and you're left just with the unit of watts for power. Does that make sense?
Yeah. So
lastly, just so that's something you have, power is measured in watts, normally just written W. Intensity is measured in watts per square meter. which is normally written as W/m squared, like that. And then area is the square meter. So those are the units. And then sound level, what's called sound level. What are the units for sound level?
Sound level?
Yeah, it's called the sound level. That is the decibel. So when you say 20 decibels, 30 decibels, 50 decibels, that's called the sound level. Okay?
Okay.
So I think we're just about out of time. Let me just peek if there's any quick hints I can give you. So for 26, it says, what would you estimate the length of a bass clarinet to be? Assuming that it is modeled as a closed tube and that the lowest note that it can play is a D, whose frequency is 69 hertz. So this, once you start these problems, it kind of shifts gears and you start talking about sound waves inside of instruments, but not on strings. Now it's like wind instruments. It's the sound waves in the air inside the wind instrument.
Okay.
And so let me just point out that from our last lesson, the wavelength for a string that's vibrating is 2L over N. You remember that?
Yeah.
And N is the harmonic number, 1, 2, 3, 4. And so when you have a tube that's closed at both ends, if it's closed here and it's closed here, you get a wave that looks just like the strings that we talked about before. Remember this one that can go up and down like this?
Yeah.
That's N equals 1. That's the fundamental harmonic. So in this problem, number 26, when they tell you that the frequency, if they don't tell you what the harmonic number is, if they don't say N equals 3 or N equals 5, then you always assume that what they're reporting to you is the fundamental, N equals 1.
Okay.
So in that problem, you're utilizing this formula right here to estimate the length, which would be L, of this instrument based on the fact that they're telling you that the wavelength, well, actually, they didn't tell you the wavelength. How would we figure out what the wavelength is? All they gave you was the frequency of the wave, frequency of the sound. So what formula would tie frequency and wavelength together?
Wavelength equals frequency equals times velocity.
Yeah, that's close. So it's actually velocity equals frequency times wavelength.
Velocity.
And so remember that for normal air, if they don't know, say it's a problem, like like it was before, then you always assume that they're referring to 20 degrees Celsius, which is 343 meters per second, is the speed of the wave, speed of sound, air at 20 degrees Celsius. So if there's no mention of temperature, you will always assume that you're using the value of 343 for the speed of sound. And so you always know that. They've given you the frequency of 69 hertz, right?
Yeah.
So could you solve for the wavelength? Could you solve it? I said, could you then solve for the wavelength?
Yeah.
Yeah, you have 343 here. You have 69 here. You could solve for the wavelength, and there, where would it go? Here. See that? What value would you stick in for N? If they don't mention anything, then you assume it's the lowest possible frequency called the fundamental, which is N equals 1.
Okay.
And so in that way, you can solve for L.
then you do the inference of that. And suppose L equal 2.
L will end up equaling lambda divided by 2.
Lambda divided by 2.
Yep. And you would have to figure out what lambda is from this equation over here first.
Okay.
I don't think I want to give you too many others, but if you wanted, again, to send me your problems, if that's something you wanted to do, I could look them over before you hand them in. I don't know if you get graded on them or not. Do you get graded on your homework? Like, does your professor come to your homework and look at it, or how does that work?
He does.
And does he actually, like, correct it for you so that if it was wrong, he would show you how to do it correctly?
Yeah.
Oh, he does. Okay. But nonetheless, do you get a homework grade based on being correct or not correct?
Yes.
Oh, okay. So if you ever wanted to do your best effort and then send it to me, I could always go over and get back to you if you wanted. Okay? You don't have to. It's just I'm just offering that to you.
Yeah, okay.
So I think that that leaves three for you: 34, 36, and 48. I hope that was helpful.
Yeah, thank you very much.
All right, you're welcome, and I'll catch up with you next week. All right. All right. Bye, Jeremiah.
All right. Bye.
Bye. Okay, that concludes our session for tonight, which is which day? March 5th, 9:05 p.m. Just finished with Jeremiah, Boston Dream Academy, talking about sound energy and sound waves through air.